I'm Ningning from the University of Toronto. It's an honor to be here to give a talk on my recent work on smart handlers handling the selection monad. This is joint work with my collaborator, Golden Plotkin. So this talk is going to be about decision-making processes. So whether you like it or not, we make lots of decisions every day. For example, whether to drink coffee or tea for the breakfast, or which password to use when you set up an account, or whether you would like to accept or reject a specific paper if you serve on a conference program committee. And it would be really useful if we can model this kind of decision-making processes as programs, so that we can express decisions as computations, and we can program with them and reason about them. And in order to do that, we would need the program to be able to express decisions as choices and capture consequences of choices, and then based on the consequences of choices, define optimization strategies. As a concrete example of such kind of decision-making programs, consider implementing a binary search algorithm that searches an ordered array A for a value X. And this slide shows the type signature of the program, where B search takes a value X and an ordered array A and the ranges of the array to search for left L and right R. And for simplicity, we would assume the value is always in the array, so the searching is always successful. And hopefully you still remember how to implement this algorithm from your algorithm courses. So the program would go like this. So first, for each iteration of the program, we would split the array into two halves. And then we compare the element at the middle of the array, AM, with the value X. If AM is equivalent to X, great, we are done. Or otherwise, depending on which value is smaller, we will do a recursive call to B search with updated range from M+1 to R if AM is smaller, or otherwise from L to M-1. So in other words, the essence of this algorithm is that for each iteration, we compare X with a specific element at index M to shorten the range of the array in which searching must be performed. And a natural question to ask then is, which index M should we actually use for each iteration? And in this case, we have always used the element in the middle of an array, but this is actually really a choice that we can make differently, right? Like consider, for example, if X is really, really small and the array contains a lot of large numbers, then maybe for each iteration, we can be a little bit more aggressive, smaller indices, so that we can perform fewer recursions to get more efficiency. And in order to capture this kind of choices, smart choices is a set of APIs basically used at Google, which can be used to implement binary search like this. And these APIs, they allow programmers to provide choices, contexts, and feedback to the underlying server. And in this case, the choices are basically an integer number from the range L and R, and the contexts include the value X and the values of elements at both ends of array. And the feedback is basically the program has to pay to recurse. So the underlying server should learn to perform less recursions in order to get better optimizations. And in this particular case, we would expect the server maybe to perform some training and deploy policies for making decisions in order to avoid payments. For example, a clever choice can take into account the distribution of the data and the records of past decisions in order to decide how to better select M for each iteration. But this is just a particular set of APIs. And in this talk, we would like to study this kind of decision-making abstractions using a more general approach and from a PL perspective. More specifically, this talk is about the marriage of two programming language features to support two key components in decision-making processes. First, there may be numerous choice operations in a program which can depend on various context information, complicated computations, or maybe even one choice can depend on other choices. So we need a way to express composable and modular user-defined operations. In order to do that, we use algebraic effect handlers, which allows for choice operations to be defined as user-defined operations that can be then handled separately using effect handlers. And at the same time, we also need to model computations that involve making choices. So we take ideas from a monad called the selection monad, which enables handlers to choose computations based on the losses the potential choices entail. And we call the resulting effect handler systems smart handlers, as these smart handlers empower programmers to write decision-making programs using choice operations, which can then be handled separately by applying different optimization algorithms implemented as handlers. So for the rest of the talk, I will first give a taste of smart handlers through an example, and then I will define a model calculus that defines the semantics of our design. And finally, we will see some more examples implemented using smart handlers. And let's start with a taste of smart handlers. To do that, I will first provide a brief background on algebraic effect handlers, and then I will show how the selection monad can be added to the system on top of effect handlers. And we start with the background on algebraic effect handlers through a simple example. So intuitively, effect handlers are a powerful way to incorporate computational effects in a programming language. And for this particular example, we consider an effect signature that defines an effect operation decide that takes a unit and returns a Boolean. And with this effect signature, we can already start programming with these operations. For example, we can write a program F that performs operation decide, and in this case, twice. Specifically, F performs the operation decide by providing an argument to this operation, in this case, just a unit. And F performs effects twice and returns the result of the AND operator taking these two variables. And this program has no idea at all how decide is going to be actually implemented, because the semantics of effect operations are actually provided by effect handlers. So we write this with handle class to handle the computation F using a specific handler, in this case, a handler for decide. And the handler defines what happens when an operation is performed. In this case, decide maps to a function that takes the argument to the operation, in this case, just the unit, as well as a continuation that captures from where the operation is performed to where the handler is used to handle this operation. And in this case, the handler performs the continuation k twice with true and false respectively and concatenates the result. And the return clause is applied when the computation returns normally. So in this case, if the computation returns a result X, then the return clause simply wraps the result into a singleton list. And that's why also the return type of K is a list of Boolean now. So if we actually run this program, we would get a list with 4 elements: true, false, false, false. That corresponds to the case when X is true, Y is true, and X is true, Y is false, and X is false, Y is true, and X is false, Y is false. And only the very first element would be true. So I hope this example provides an intuitive explanation about effect handlers, where the syntax and semantics of operations can be decomposed and defined separately, so that we can do more modular programming, where we can, for example, write a set of operations in a single program, or we can nest the effect handlers in different orders to handle operations in a program. So with the background of algebraic effect handlers ready, we can now demonstrate how the selection monad can be useful. And let's demonstrate that by considering another example. So imagine we are registering for an account at a website where we need to set a password. And of course, there is a set of criteria for the password, but those criteria are not very important for our example, but they are just there. And let's consider that we want to model this process of picking a password as an effective program, with the idea being that we want to define an operation pick that takes a list of password candidates and returns the chosen password. And with this effect signature, we can now already start performing the pick operation in our program. For example, maybe we would like to pick a password from this list of 3 candidates, Hello World, HOPE'25, and Singapore. And of course, as with effect handlers, the program does not know how this pick operation is going to get handled. But very importantly, the program wants the handler to know that there is certain losses associated with each choice, or costs associated with each choice, right? Like, for example, maybe we want the password to be as long as possible. So depending on the length of the password, we would incur a loss, which is a negative result of the length of the password. So a negative loss can be considered as a reward, right? Because losses are due to rewards. So we are basically rewarding longer passwords. And maybe also we want the password to contain as many distinct elements as possible. So there is some Haskell functions that calculates how many distinct number of characters there are in a string. And then it also incurs a loss, which is the negative result of I squared. And the hope is that, the handlers can take into account those loss informations when it makes the decision for which password to use. And here, the loss operation can be considered as a built-in operation that basically corresponds to a writer. So we are writing to the handler what losses that will occur for each operation, for each choice of the password candidate. And then the program can just return the password that is chosen. Now, let's try to define a handler for pick. And of course, we can define different handlers. And here, let's consider a greedy algorithm that picks a password from the list that minimizes the loss. So let's try to implement the handler. So in this case, the handler for pick will receive the list of strings as PS and then the continuation K. And we can start by filtering out those passwords that do not satisfy the criterion, right? But again, those set of criteria do not really matter for our example. But now we have a problem, which is what happens afterwards? Or how can we actually implement this handler? Right? Because to implement our desired semantics that we would like to make a decision to minimize the loss, we would first need to know the loss associated with each candidate. But we do not have that piece of information available when we define this handler. And this is how the selection monad comes into play. And the selection monad basically models computations that involve making a choice. And this slide gives the definition of the selection monad. So S of X is basically a higher order function that takes a selection from X to R and returns an X. And the interpretation of this monad is that if you can tell me how X affects R, then I'm happy to pick an X for you. And we can consider some of the examples that maybe you have encountered in your program, based on your programming experience. For example, argmax is a function that has this type, and argmax basically returns the arguments at which a function output value is maximized. And you can also consider an operator called exists that tries to find at least one element that satisfies the function x to r if r is, for example, a proposition or a Boolean value. And if you are familiar with continuation monad, maybe you have noticed some similarities and differences between selection monad and continuation monad. And in the case of continuation monad, the monad will go from x to r, and the selection monad goes from x to r to x, because in the continuation monad, you care more about the final result of the continuation, while in the selection monad, you care more about which element we have selected. And of course, if we have the elements available and we have the selection function, we can still recover the final result of the computation. And if you know continuation monad, of course, you know continuation monad is a monad. And the selection monad apparently is also a monad. And to show you that this is the case, let's actually try to define the return function and the bind function for the selection monad. And one advantage of programming with types is those definitions are basically very straightforward if we just follow the type signature. And there are basically no other choices we can make in this definition. What do I mean? So let's look at those definitions and try to first define the return function for the selection monad. So the return function has this type signature. It takes an x and returns sx. So let's define the definition of return. Of course, it is a function, so we know it takes an x. And it needs to return something of type sx. And we know sx is x to r to x. So we have another function, gamma, with type x to r. And now we need to return x. Then what should we return? There are no other choices, right? We will just return x. And the bind operation is slightly more complicated. So in this case, the signature goes from sx to x to sy, and it returns sy in the end. But again, let's just follow the type signature and try to write out the definition. First, it is a function. So we have capital F of type sx, and this little f of type x to sy. And now we need to return sy. And sy is the function from y to r to y. So we know that we are going to have a gamma y to r, and our only job left now is to construct a y. We know how to construct the y because we have f available, and f is the only function that returns the y in the end, right? And we can apply f as long as we provide it with a value x and a function from y to r. And we do have the function from y to r, which is gamma, and now we only need to construct x. And looking at the context, the only way we can construct an x is calling this big F, as long as we can provide a function from x to r. Since it is a function, of course, we can take an argument of type x and now just need to return r. And the only way we can return r is by applying gamma if we can provide a y, right? And now we are back in the situation where we need to provide a y, but in this case, we have an x available already, so we can just call f with x as well as the function gamma from y to r. So as you can see, right, following the type signature, we can write out the definition very mechanically. And although the function might seem quite complicated, the intuition behind this is, right, this function is basically just trying to get a loss value based on how x affects y. And this is how the selection monad trains a list of computations. And more interestingly, we can also combine selection monad with other monads. And for example, we can combine selection monad with the writer monad, where the writer monad is just the standard pair of r and x, where this r is the same r as this x to r. And this writer monad basically provides semantics for our loss operations. Like, as I said, this loss operation is really a writer operation that tries to write and accumulate losses. And our final selection monad that we actually use in our semantics is slightly more complicated than this because we also need to take into account the set of effect operations that are not handled because we are working with effect handlers. And we'll get back to this definition when we talk about selection when we talk about the denotational semantics if we have time. All right. So now that we have introduced the selection monad, we can actually go back to our definition of the greedy algorithm for pick, and let's try to finish it by applying ideas inspired by the selection monad. And the key idea now is in the operation clause, in addition to the argument PS as well as the continuation K, the handler now receives another continuation L, which we call the choice continuation. And if you compare the choice continuation with continuation, you can see that they both accept the return result of the operation, but different from continuation, choice continuation always has the return type a real number, which denotes the loss associated with the choice. And if we have this choice continuation available, then we can continue writing the definition of the handler, where we basically just call this mean width function, which takes the function and a list of arguments and tries to pick from the list of arguments a value that minimizes the function L. And once we have picked the password, then we can just resume the original computation by calling f with p. So this is basically the handler we'll be using for picking our password. And a particular thing worth noting is that in this system, we actually have two continuations, right? So we have this continuation K that is delimited because it captures from where the operation is performed to where the handler is used to handle this operation. And we also have the choice continuation, that L, which is global by default because it calculates how the loss affects the rest of the whole program. But of course, we have also provided additional language constructs that can help you delimit the scope of choice continuation if you want. So we actually have a more general setting where the continuation is global by default, but can be delimited if you want. And the continuation K is basically taken from standard effect handlers, right? And the choice continuation is the new continuation that corresponds to computational ideas derived from the selection monad. And we can also look at the types of these continuations, and we can observe similarities and differences. So if the operation is an operation that goes from A to B, then the continuation would have type B to the type of the program, which is the type of the whole handler program. While for the choice continuation, it would always go from B to a real number because the choice continuation is supposed to tell us what loss is associated with each choice of the operation result. All right. So I hope that gives you a rough feeling about what we can do with smart handlers now that we have this loss information available. And before we see more examples, let's look at a minimal model calculus that defines the semantics we want of our design. So we will start with syntax. And the syntax of the expression includes, well, constants and primitive functions, and also constructs that correspond to a lambda calculus. We have variables, we have functions, and we have applications. And because we are working in an effect type system, so the lambdas are explicitly annotated with effect annotation that tells us what effect can occur in the body when this function is applied. And we have three constructs associated with effect handlers. So we can perform an effect operation op by providing an argument E. And we can also call the loss operation by providing an argument E. And we can also handle a computation E using a specific handler H. And as I stated, this loss operation is basically just a writer operation that writes the loss. So if you call the loss continuation multiple times, the losses will get accumulated. And we have three constructs specifically for ideas inspired by the selection monad, where this first form is really just an internal form that occurs during evaluation. So this is not a user-facing syntax, but it is very important that gets us the semantics right when we evaluate a program. So we would pronounce this triangle operator as then because it basically accumulates losses. So it will first evaluate E1 and then collect the loss of it, and then pass the result of E1 as X to E2 and calculate further losses from E2. And the last two constructs are the scoping constructs that we use that can be used to delimit the scope of losses and the choice continuations. And we'll get back to them when we talk about the operational semantics. And we can also define loss continuation expressions, which are basically loss continuation expressions corresponds to the function from X to R in the selection monad definition. So it takes a value and calculates a loss. So it only has two forms. It is either a zero loss continuation, so evaluation of every program will start with a zero loss continuation, or it is extending a loss continuation with another loss continuation expression. And this extension will happen during evaluation so that we can capture the loss information for a particular program result by extracting information from the rest of the program. And we will talk more about how those constructs are built and extended when we talk about operational semantics. And lastly, we have the syntax for handlers. And the syntax for handlers is mostly standard, except that the handler classes, the operation classes now can take this additional choice continuation as an argument. And a handler might handle multiple operations and define an optional return clause. And in this case, the syntax is a little bit verbose just because we are programming with explicit types and effects. So everything has explicit effect annotations that tells us, for example, what effect might occur when a function gets applied. But all those effect annotations are not that important to our operational semantics. And this is the complete set of syntax, right? We have basically expressions corresponds to the lambda calculus, to the effect handlers, and corresponds to things that we can use to manipulate losses and choice continuations. And with the syntax ready, we can now talk about the type system and the operational semantics. And the type system is mostly trivial. It is just used to make sure the system is type safe. And the operational semantics will be more interesting where we see how those loss continuations are built. So let's start with the type system. So as I said, the type system is actually quite straightforward. So we have base types or a function type. And for a function type that goes from sigma to tau, we need to record what kind of effects that can occur when the function is applied. And the effect epsilon is a set of labels, so it can either be empty or we can extend an epsilon with an additional label L. And we have the normal typing context that tracks the type of variables, and we have a global operation context that defines what operations and what their types are for each effect label. And the typing judgment is just like the typing judgment for any effect type system, where under the typing context the gamma, this expression E has type sigma and might perform effects in epsilon. And all these the 5 rules on this slide, they are very standard typing rules for the lambda constructs in effect type system. And one particular thing that might be worth noting is again, because we are working with effects, the function type needs to track the effect of the body. So if in this case E can perform effect in epsilon, then the return function type will need to remember that the function can perform epsilon when it is applied. And we'll skip all the other rules because they are fairly standard. And let's get to the slightly more interesting ones about effect handlers. So we have 3 rules corresponding to the effect operations, right? We can perform an operation op by providing an argument E. And if we perform operation op, then we should record in the returned effect epsilon that we have performed this operation op that corresponds to the effect label L. So this net condition makes sure that L does appear in epsilon. And on the other hand, when we handle an expression using a handler, then the handler can eliminate one effect label from the effect information of the expression. So if E has effect epsilon L, then after E is handled, then the effect left is just epsilon. And the loss operation takes a real number, which is E, and itself just returns a unit because its job is just to record this loss information, and it has whatever effect that this E says it has. Right. We get to more interesting typing rules when we talk about constructs corresponding to the selection monad, right? For example, we want to type check then. So as I said, then works by first evaluating E and then pass the result of E to E2, basically binding the result of E1 to X when type check E2. So E1 has the same type as X. And local works similarly. So this E has this type epsilon, which is going to be passed to this loss continuation G that will take the result of E and calculate the loss L, the loss R. And all those set conditions on the effects, they are basically just needed for type safety. So we will not be worrying about effects too much when we talk about operational semantics. So this is just to show you this type system exists. We have typing rules corresponding to each language construct we have in the characters. And our last typing rule is reset. So reset just slightly changes the semantics of E, but in terms of typing, it's very trivial. It just has the same effect and type as E. So like I said, this type system is mostly trivial. We just need those typing rules so that we can prove type safety of our calculus. And it's a very standard type system as most effect handler systems. And the more interesting bit is actually in the operational semantics of these effects. And the operational semantics is also one of the most complicated bits in our system. So this is how the evaluation judgment looks like. So it reads that under a loss continuation G, E evaluates to E prime and producing a loss R. And the actual operational semantics is actually also associated with effect information. But from now on, we will be just forgetting about all those effect informations and instead focusing on the behavior of the program during the operational semantics. And intuitively, this loss continuation G corresponds to that function X to R in the definition of the selection monad. And this is how our semantics is built. So let's now look at some of those operational semantics rules that maybe help you understand a bit better and deeper about how this system is working. So we will start with 2 standard rules. If we want to evaluate a primitive function f, then we will assume some built-in evaluation rules for f. And evaluating a lambda applied to a value is just one step of beta reduction with a substitution. And both rules, they just have 0 loss, right? Because there is no loss to be recorded. And the language construct that will start building loss from the beginning, right, is the loss operator that takes the expression R. And in this case, we are focusing on when R is already a value, but of course, our system has all those congruent rules that evaluate expressions on the evaluation context. So if R is already a value, then what happens? Well, the return type of loss is just a unit, so we just return a unit. But we would remember that we have produced this loss R in the operational semantics by keeping track of this R in the operational semantics. And this is basically the only rule that produces loss, and the loss will keep being propagated throughout the evaluation of our program. But this is the only construct that could produce a loss value. And we would omit lots of other evaluation rules, but let's focus on the most interesting one of this system, which is the evaluation rule for handlers. So if we want to evaluate this computation E under this handler H, then what should we do? Well, it depends what happens with this E, right? Because there are three cases. Maybe E returns a value already, or maybe E performs operation that needs to be handled, or maybe E itself sets, right, under the handlers. So we will have to define three operational semantics rules corresponding to each of these three cases. Let's start with when E returns a value. So if E returns a value, in that case, we will just get the return clause from the handler. Let's say it is VR, and we just apply VR to V. And we also produce a zero loss because there's no loss produced with this step of evaluation, right? And more interestingly, what happens if E performs an operation? So this is the actual very important bit in the semantics that gets us the choice continuation and get our examples to work. So if E performs an operation, and in this case, we are trying to find the handler that will handle this operation. So we write this capital K as evaluation context that sits between where the operation is performed and where the handler is, which is the handler that we use to handle this operation. And there are side conditions that make sure that we use the innermost corresponding handler for this operation, because you might have multiple handlers for this operation, right? And we want to use the innermost one. And once we have found the innermost operation, innermost handler for this operation, we just get the operation clause, in this case VO, and we apply VO to three arguments. V is the argument we provide to the operation, and L is the choice continuation, and K is the continuation. And of course, we need to define what K and L are, right, for this rule to work. So intuitively, K corresponds to the standard delimited continuation for effective handlers, where we capture, again, from where the operation is performed to where the handler is used to handle this operation. So it just resumes original computation once it receives a return result Y. But an additional bit of complexity in our system is that we actually needed to do a little bit wrapping around this continuation, because we do not only need to remember, we do not only need to capture the continuation, but we also need to remember that this continuation is captured under that loss continuation G. So this bracket is one of the language constructs that helps delimit scope of choice continuations. In this case, we just want to remember that this expression is captured under the loss continuation G. So whenever we resume this computation, that reception should be evaluated under the loss continuation G as well. And the choice continuation, right, is one of the most important bits in the operational semantics. It looks very similar to the continuation. But instead of local, it uses this triangle operator to actually calculate the loss of the continuation that is associated with the operation result Y. So if you give me a loss, give me operation result Y, then I will use this Y to calculate what losses will occur in the rest of the program. And of course, I need to do a little bit more because this program is evaluated under the current loss continuation G. So I also need to pass the result to the loss continuation G, actually calculate the loss. So intuitively speaking, this is how we calculate the loss associated with each operation result. And we still have the last case, which is when E steps under the handler H. And normally, right, if E steps E prime, then of course with H handle E will evaluate with H handle E prime. But additional complexity in the operational semantics rule is which loss continuation should we use to evaluate this E? We know that this with H handle E, this whole expression is evaluated under the loss continuation G, which is waiting for the result of this expression. But the G is not waiting for the result of E, right? Because when E returns, we know that the return clause of the handler will get applied first. So that is why we need to extend the loss continuation when we evaluate E. So the loss continuation under which we evaluate E is not G, but it is first applying the return clause VR from the handler, and then we pass the whole result to G that is actually waiting for the result of this whole handle expression. And you can see this is how the loss continuation gets extended during evaluation of the program. And our last bit of complexity in the operational semantics is just to define the operational semantics for then, right? What happens actually when we call then? So intuitively, then is just accumulating losses. So if we evaluate E, if E steps to E prime and produces a loss R, then this rule must accumulate the loss that is produced by E, by evaluating this E. And of course, E prime still needs to get evaluated under G prime. And the semantics, this rule itself produces a zero loss because the whole purpose of this then operator is to calculate a loss value for the operation, and itself does not incur any loss. And if E already reduces to a value in the end, then we would just evaluate this E by passing the value of V to E by binding it to X. And again, because this whole thing just produces a zero loss, we put this local construct. Remember that this whole thing produces zero loss by itself, because the whole purpose is just to calculate a real number that actually represents that loss. And lastly, we have the rule for local, and it's actually very intuitive. So if we want to localize a loss continuation for G, then that just means we will change under which loss continuation E is evaluated. So it changes from G to G1 in this case. And if we want to reset an expression, that just means the loss information from E will not be propagated to the outside. So this expression in itself always produce a zero loss. Then it allows us to localize loss information. And that's basically all the operational semantics rules, right? All the most important ones. And as I said, of course, we have more rules that will evaluate things under evaluation context, but these rules have captured the essence of our system where we handle operation with the handler, and we talked about how the loss continuation gets extended during evaluation and how the then operator accumulates the loss information. And with that, we can now go back to our example of picking a password and actually see how this program gets evaluated. So we would always start evaluating expression under a zero loss continuation, right? So let's assume this whole program is evaluated under zero loss continuation. And we are evaluating a program under a handler. And the first statement we need to evaluate is this pick operation, right? And because we are performing an operation, this is where we should apply the handle rule that handles this operation. And if we want to handle this operation, we will get the operation clause of pick from the handler and bind PS and L and K. So in this case, I have also put the dimension of K and L on the bottom of the slide. So we will start by filtering out the passwords that do not satisfy the criterion. And again, this specific criterion do not actually matter. And in this case, let's assume you always need a special symbol in your password. So let's rule out Singapore first. And then PS prime is just the hello world and SFP25. And we can now call this function mean with the loss continuation L and the two candidates hello world and SFP25. And the implementation of mean width is basically just enumerate all the choices, right, and gets the element that minimizes the value of L. So let's start by enumerating all the choices we have. So in this case, we have hello world and SFP 2025, and let's start with hello world. So if P is hello world, right, and now we can actually evaluate the loss continuation and try to see what loss value we would get in the end. And in this case, the handler H doesn't quite matter, so let's just ignore it. And then we calculate the loss value. And the first value we would produce is the length of P, or the negative of the length of P, right? And this whole thing is still evaluated under this right triangle. So we need to apply first the Zen rule that allows us to accumulate losses. And in this case, the length of P, or the negative value of it, is just minus 12. And then we keep evaluating the rest of the program still under the same triangle operator. And our second loss is just the square of how many distinct characters are there in a string. So I have done the calculation for you, so you can trust me on that. And then we just need to calculate the final string. And in this case, the loss value is just 0. So the final result would be minus 12 plus minus 81 minus 0, which is minus 93. And this is the loss we would get when P is hello world, right? But we also have another option, which is when P is ICFP25. So I have also done the calculation, and in this case, if P is ICFP25, then we will get minus 8 plus minus 64 plus minus 64 plus 0, which is minus 72. And we compare these two loss values, and we realize, the loss for hello world is lower, so we should resume the original computation with P being hello world. And if we resume the original computation with P being hello world, then we can produce the final result, which is password is hello world. So hello world is the safest password, right? You should use when you register account. And this whole computation, of course, itself produced a loss minus 93. So this is an example where we make use of the choice continuation to allow the handlers to actually pick a particular password based on the loss information, right? And now let's see more examples and what other things we can do with smart handlers. And so in the case of picking your password, right, we basically just enumerated all the choices and try to get the one that produced the optimal result, because we are applying a greedy algorithm, right? But in practice, of course, it's not always possible to enumerate all the potential choices and identify the best one. So we look at another example for optimization algorithms, and we consider the simplest form of linear regression. And for linear regression, basically, we want to find a linear relation between two variables given a data set of x and y, right? And if we have this data set, then the goal is to find a weight w and a bias b so that the linear function best models this relation. So in this case, I have x being the novelty of your paper and y being the acceptance rate of the paper. And of course, the data is completely made up. So we can represent this linear regression problem, right, as an optimization program in which we can gradually refine the parameters by applying optimization algorithms. So what we will do is we will start by defining an operation optimize that takes the current parameters and returns the updated parameter. And similarly to our set a password example, with this effect operation, right, we can already start programming with this effect operation. So let's try to define the program that does linear regression with respect to the current weight W bias B and a data point X and Y. And we will co-optimize by passing the current parameters W and B, and somehow we expect optimize to return the updated parameter W prime and B prime. And if we have the updated parameter, then we can actually calculate the predicted Y prime using those parameters and X, right? And now, any differences between Y and Y prime is the corresponding loss for this parameter. And in this case, is the square of the difference of Y and Y prime. And once we get, we have passed the loss information, then we can just return the updated parameters W prime and B prime. And now a more interesting question right now is how this optimized operation should be handled. So we would like to apply optimization algorithms simply by defining handlers for optimize. And in this particular case, we would apply a stochastic gradient descent, which is a widely used method for iterative optimization. And the idea is basically starting from some initial parameters. The gradient descent would minimize a cost function by repeatedly updating the parameters in the direction opposite to their gradients. And we can do this step after processing each randomly selected data point. So now we can implement gradient descent as a handler. And this handler receives the current parameters PS and the choice continuation L and the continuation K. And it can start by doing a step of automatic differentiation that calculates the gradient of L with respect to PS. So we would assume autodiff implements automatic differentiations. Of course, in languages with built-in support for automatic differentiations, this would be even simpler. And now that we have calculated the gradients of the function with respect to the parameters, we can update the parameter by performing one step of gradient descent. And we would assume alpha is the learning rate, so we can update the parameters to be PS prime by moving in the opposite direction of their gradients. And once we get PS prime, we can just resume the original computation with PS prime. So in this case, we just handle linear regression once, but of course, in practice, you would actually have a whole training loop, right? You would apply this handler to each of the input data, and if you have a while loop, then it's actually very useful to have those scoping constructs that can delimited, for example, choices within each iteration. So one iteration, the choice from one iteration does not affect the next iteration. And this is an example where we implemented optimizations as handlers, as smart handlers that make use of the choice continuation. But in this case, there is something that is not very satisfying, which is this magic number for the learning rate, 0.05. So let's consider another example where we do hyperparameters. So basically, those parameters like learning rate is considered the hyperparameters because they control how the training algorithm is performed. So instead of just encoding this magic number 0.05 in the handler, what we can do is, because we are in an effect handler system, we can abstracting this operation just to be an effect operation that returns a float value for us. So let's say L rate is just an operation that takes the unit and returns the float. And now we can abstract over the learning rate from the handler by performing L rate and passing the argument unit, and the result is bound to alpha. And we can, of course, recover our previous behavior by basically just implementing a handler for error rate that always returns 0.05, right? And this is basically just a reader handler that whenever you call error rate, it's going to get you the same value. But a more interesting example of handler, and because we are in an effect handler system, we can actually handle the same program using different handlers. And a particular handler, and another thing that we like to note is, in this case, right, we basically just use the continuation K, because this is more or less just a standard effect handlers that does not use the choice continuation, but just resumes the computation with 0.05. And a more interesting handler in this case would be a handler that performs what people call hyperparameter tuning. So that basically means we would resume the loss continuation multiple times, in this case, maybe with 0.03 and 0.05 respectively, and we compare the loss value we get from these two loss continuations. And depending on which one is smaller, we would return the better hyperparameter. And this handler is also interesting because this is a handler that, in contrast to the previous definition, this handler uses only the choice continuation. It's not. It's not interested in resuming the original computation because the point of this handler is to get a better hyperparameter in the end. So it just compares the loss produces on the different hyperparameters and uses one that produces less loss. So as a final example, we would consider two-player games. It's also another kind of smart handlers we can write. So let's consider Alice and Bob are playing a game, and each of them can make a decision between left and right. Alice performs first, and Bob performs next. And then the loss is just returned by looking up in a loss table. And let's assume this is the loss table we would be using for this example. Of course, Alice and Bob, when playing the game, right, we don't know the strategy each player is going to use. And the playing strategies are also going to be implemented as effect handlers. And let's assume, in this case, Alice wants to maximize the loss, and Bob wants to minimize the loss. Then this basically corresponds to a mini-max game, right? And if you actually look at the loss table and reason more carefully about what would the result be returned in the end, you can actually follow the operational semantics, and you will see that because Bob wants to minimize the loss, so when Alice performs left, Bob will perform right. And when Alice performs right, Bob will perform left because Bob wants to minimize the loss among the two choices. On the other hand, Alice wants to maximize the loss. So from the rest of the options, Alice will actually perform left because 3 is larger than 2. So we get a better loss information produced by Alice. So again, this is another example of smart handlers. And one particularly interesting thing about this example is, in this case, these two handlers, they're actually sharing the same loss, right? But they're applying different strategies in what they want to do with loss. So Alice tries to maximize it, and Bob tries to minimize it. And I hope all these different examples, give you a flavor about what we can do with smart handlers and all the different kind of strategies one can implement as effect handlers. So we are slightly running out of time. So there are more things in the work that I did not have time to talk about. For example, we have one more example that is also related to gaming a bit. So it's Nash equilibrium. And we have this example available in the paper. And in the paper, we also prove type safety. So we prove that operational semantics is deterministic, and we prove standard lemmas like progress and preservation. And we also have defined a denotational semantics that we proved to be sound and adequate. So the denotational semantics and operational semantics actually correspond to each other. And additionally, we provide a Haskell implementation of this whole language design, where we define a selection monad and use it to do programming. So all the examples that I demonstrated, they are implemented using the Haskell library. So they are actually all implementable. That shows, what kind of interesting things you can do with the selection monad. So I will probably skip the rest of few technical slides, but you can see more about them in the paper. So there is some reasoning about termination of the calculus. So if you just work with standard effect handlers, actually you can write a non-terminating program. And in our case, we would actually be impose a limitation of this effect system, and under this limitation, we can prove that the calculus is actually terminating. And this is the assumption we had on the effects. It's what we call well-foundedness of effects. And under this assumption, we can establish termination for the calculus. And here are a few slides on the denotational semantics. If we are interested, we have a whole section on that in the paper. So this is the selection monad that we actually use in the end. It incorporates what people call interaction trees, or those effect operation trees, where everything is basically a tree that each node is an operation that can be handled by a handler. And in our case, we also needed to take care of the selection monad. And this is where you can see the selection monad comes into play. And there are more definitions, but in the end, we proved that this denotational semantics is sound and adequate. So in the rest of the time, actually in the last just 2 minutes, I will talk a little bit about what we plan to do next for this work. So in this talk, I have presented a fairly complicated direct operational semantic for this system, and this is actually how we implemented it. But in practice, maybe what you want is a translation of effect handlers with choice continuations down to just the standard effect handlers, right? And that is useful because now you don't have to change the operational semantics of your language, but you can implement the semantics on top of existing programming languages that support effect handlers. And for this work, we did not support effect polymorphism. So every effect epsilon is just a set of concrete labels. But we do not see any fundamental challenges in extending the calculus with effect polymorphism. Especially, there's a lot of work already in the literature that support effect polymorphism for effect handlers. And our Haskell implementation is more a proof of concept, right? It provides a prototype and which we can program in, and we actually use it to implement all the examples. But if we want to actually do something more serious with it, we are currently trying to have implementation in the JAX programming language, which is a Python library for accelerator-oriented array computation and program transformation. But what's interesting about JAX is basically it's a functional domain-specific language embedded in Python. So it has lots of functional programming flavors, although it's a DSL written in Python. And it's somewhat well known in the literature that selection monad itself is not very efficient. So we are trying to incorporate what people do in existing work to improve the efficiency of selection monad. And there is a paper actually pretty recent also in this year about a more efficient selection monad encoding. And if you're interested in learning more about this work, so we have this PLDI paper that you can take a look. And Gordon also presented at LAFI last year about work in progress translation of effect handlers with choice continuation down to standard effect handlers. And we also have this extended abstract at ML for Systems at Europe's 2023 that talks about a sketch implementation in JAX. All right, that's all I want to say, and thanks for your attention, and I'm happy to take questions.
all the kind of technical details there. It seems like the thing is take the parts you're making this choice off this kind of like I assume that like Jax is a pretty good motivated example. There's things like, you know, so we have to said and all that shop food work is happening there. But in practice, in user perspective, how does using these techniques in the context of Jax, how does that affect the experience for users?
Yes, that's a very good question. I think I'm asked to repeat this question. So the question is how our design affects the end user's experience, especially in the context of JAX. So you are completely right that JAX and those kind of machine learning programming was a major motivation for this work, where we would like to abstract over all those different optimization algorithms you can do for different machine learning training algorithms. And if you look at how people implement machine learning libraries nowadays, it's quite miserable. Like people repeat, copy and paste the code everywhere and change it slightly just for a slightly different logic. And maybe they apply a slightly different optimization algorithm. And the whole repository is just full of code that is repeated and copy pasted from different places. So the original motivation of this work is, well, if the thing you care the most in a training algorithm is, how to pick parameters and how to pick hyperparameters, and maybe you want to decide which training model you want to use, especially there are lots of different training algorithms, why don't we abstract over all these logics in a more abstract setting so user can just, write training algorithms without worrying about how those operations will actually get handled. And then maybe you can later plug in different optimization algorithms or handlers for parameters, and hyperparameters just are different handlers, right? And you can apply, you can handle the same training algorithm using different handlers. You can support different effects in a single program because maybe you want to do stateful operations as well. You want to do random number generation. You want to do parallelism and non-determinism maybe, and exceptions. So now you have a very unified framework to do all these kind of things. So this is basically the dream, the word that we dreamed about, right? Of course, we haven't got there. And one particular challenging that we have found during the development of this work, especially through talking to machine learning developers, is they sometimes find the concept of effect handlers overly complicated. Like not even with selection monad, just effect handlers alone. Right, it's difficult to imagine about those control flows, like things get interrupted and then things will work in a different way if your handler works differently, maybe resumes original computation twice, and now the whole stack needs to be captured, and especially if you have multiple references, and how are all these things going to work? Right. So this is still something that is currently working in progress. So we are trying to see maybe this programming paradigm is still going to be useful, but what we need is more tools to actually help the developers to understand the underlying semantics better, and to especially through development of maybe libraries or tutorials, examples, larger case studies to demonstrate that you can actually do better with this programming.
Hey, Ningning.
Hey.
Always great talk. Great work. On slide 49, you made a point about not doing the continuation, and maybe there's a misunderstanding on my side. Could you explain that again?
Sure, if I can find the slide.
So one after that. Yes, here you don't resume K, but we only use the loss continuation twice.
Yes.
How is that?
So the point of hyperparameter tuning is you're basically trying to run the program on a smaller set of data points in order to find better hyperparameters that you would actually use for real training. So here, the point is not that you would like to resume the original computation with the hyperparameter, but as long as you have called the choice continuation using different parameters, you would already produce the loss values. And then you can compare the loss values, and depending on which one is smaller, you just need to return the hyperparameter tuning. And now you get the value of the hyperparameter. You can actually apply it in a different program that would actually do the real training. So in this case, resuming the original computation is not what you want, but what you want as the final result of this whole program is just a good set of hyperparameters.
Okay, I see.
That makes sense.
This is why you're aborting the computation.
Exactly. Yeah.
Thanks.
So how baked in is the choice to use reals, the measurement for the losses? In case for the passwords, if you have a tie, you might decide to return the longest one. So maybe you need a pair of reals. Is that
Yes, very good question. So, okay, I forgot to repeat that one. But this question is about why we use real numbers as the loss, while we might want to use pairs if there are multiple loss values. So that's a very good question. So in the semantics of this work, when we define operational semantics and computational semantics, it's true we focus on real numbers because we are interested in more. First, trying to establish the foundation of this language, and later maybe we can extend it with more options. And in the Haskell implementation, actually, the encoding is happy as long as the R is a monoid. As long as different loss operations can be accumulated together. It's possible in this setting to actually, have pairs of losses, and then maybe you want to do things differently, and especially you want to find, maybe there's no best choice, but you want to find a pair of options that tries to optimize in a certain way, or maybe it's in the end like a weighted sum of different losses. It's possible in the implementation, but it's not yet possible in the semantics, but we are very interested in doing that in the future.
Great. So, I'm wondering, I guess, also from the side of what are possible applications for this, and I guess you sort of, the terminology used, the application you give, which is clearly this is geared towards machine learning. If you consider sort of applications for machine learning isn't the primary thing you're using, for instance, within a compiler, you might have some sort of black box optimization, something like that. Have you considered those sort of things? Is that something that your goal, for instance, to make it easier to use like an ML model within a compiler, the other kind of black box optimization?
Right. That's a very good question. So the question is, if you think about compilers, will this programming paradigm maybe be useful as well? I think the answer is potentially yes. And we are very interested in also trying to find more applications of this programming paradigm. We started with machine learning programming because this is how we get into this work. But I could also imagine, like in processes where you have those decision-making processes, or where you would like to potentially apply different optimization algorithms by accumulating loss informations, I think this paradigm can be very useful. And I'm very keen to know more about what kind of compiler optimizations you might have in mind, because we were definitely interested in thinking about more applications for this.
cool?
Perhaps more technical questions. So if you interleave pick and loss, you have a choice loss, always loss, and so on. Right? And then, for example, in this password example, it will globally optimize across all choices. Right? But could also the first choice have access to the current loss to apply some heuristics, could store some eagerly?
Can you repeat the question?
Yes. You have a choice and then loss, and then choice and then loss. In the first choice, observe the current loss.
Can the first choice observe the current loss? Yes, it will always receive whatever loss that comes from the rest of the program. So it will receive both losses. And while I believe the second choice would actually only observe the last one, because what happens before you does not matter. It's not what you can affect. And you can affect what happens afterwards. Cool.
Yeah, so I have a question about something I guess would be called time traveling. So it's like when in your picking example, you have a loss after the choice, and it's effectively that all the other unpicking choice got canceled. So it's like after you specify the loss, you type to the choice, and you dictate that this choice is picked, and the other choice is not. So I was wondering, that would work. Continuation computation is pure. But if the continuation performs some effect that you might not execute, like launching missiles or something like that. So you first explore all the choices, and the effects are already performed, and then you make a choice. It might be too late. So is that a problem that can be solved?
Very good question. So the question is, what if the rest of the continuation performs some effect, and then the choice continuation would have already performed those effects, which can be undesirable for the user? So this is a real problem, I would say also, or a feature of this system, which is the rest of the computation will be wrong in order to calculate the loss. And it is ran for a good reason, right? Because maybe your loss value actually depends on what kind of side effects you want to perform, right? Maybe you have to read from a file to get some value in order to calculate the loss. And maybe you want to ask for the user for some input in order to calculate the loss. So if the loss actually depends on all those side effects, then those side effects have to happen in order to calculate the loss. But it's true that maybe sometimes this is not what you desire, right? If in fact that prints to a string, right? And now the user writes a handler to handle this program, and suddenly we print twice to the string, or print multiple times to the string. And this is also an active direction that we are currently trying to explore, which is how to design the semantics so that it better fits users' intuition. Right? Like if you ask the user for some input, maybe when it resumes the computation, you should be used the same input, right? It makes no sense for getting one input to calculate the loss and then ask for a completely different input that will actually produce a different loss. And another way to make it work nicely is to limit the loss continuation to be a pure computation. Like we can actually analyze the loss continuation and analyze the data dependencies of it, and maybe you would have a strict requirement that this loss continuation must be pure in the sense that the final loss value you would get does not depend on any effect operation. Then you can just strip off all those effect operations and get a pure loss continuation in the end. So these are the possibilities that we are currently considering, but you are definitely right that in the current semantics, maybe this is not what you want, and this is, I think, currently also like an open problem we are actively trying to solve.
Is there any other question? Oh, okay, so let's speak again. Let's show where's stuff. Thanks.